Welcome! Today, we'll tackle an exciting coding challenge, problem number 2213, longest substring of one repeating character. This problem dives into string manipulation and optimization, asking us to handle dynamic updates and determine key properties of the string efficiently. Let's explore the problem, break it down, and solve it step by step. Ready? Let's get started. Along with this, there are two arrays, query characters and query indices, both of the same length k. The task is to process k queries, where each query specifies a character from query characters to replace a specific index in the string s, as given by query indices. In this problem, you're given a string s made of lowercase English letters. After each query, you need to calculate and return the length of the longest substring within s that consists of the same repeating character. The final output is an integer array result, where each element corresponds to the result for one query. Essentially, each query modifies the string, and you must determine the longest contiguous sequence of identical characters after applying the change. To understand the problem better, let's look at the first example. Here, the input string s is Babak, and the query data consists of query characters equals b, 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 and query indices equals 1, 3, 3. The output for this input is 3, 3, 4. Initially, the longest substring of repeating characters in S is AA, which has a length of 2. For the first query, we replace the character at index 1, which is A, with B. The updated string becomes Babak, and the longest repeating substring is now BBB, with a length of 3. After the first query, the result is 3. For the second query, the character at index 3, which is A, is replaced with B. This updates the string to BBBBCC. The longest repeating substring remains as BBB, with a length of 3. So, the result of this query is also 3. Finally, for the third query, the character at index 3, which is now already B, is replaced again with B, meaning there's no actual change to the string. However, this results in an extended repeating substring BBBB, which has a length of 4. Therefore, the result for this query is 4. Now consider the second example, where the input string is s equals a, and the queries involve query characters equals b, c, d, with query indices equals 0, 0, 0. The output here is 1, 1, 1. Initially, the string s contains only one character, a, so the longest substring of repeating characters is a, with a length of 1. For the first query, we replace a with b, resulting in the string b. The longest substring is now b, which still has a length of 1. For the next two queries, we continue replacing the character at index 0 with c and d, respectively. Each time, the string changes, but since there's only one character in the string, the length of the longest repeating substring remains 1 for all queries. When solving this problem, there are several edge cases to consider. First, if the string s has only one character, the result of each query will always be 1, regardless of the replacement. Second, if a query replaces a character with the same character already present at that index, the string remains unchanged, and the result for that query will be the same as the previous result. Third, for large inputs, with strings of length up to 100,000 and up to 10,000 queries, the solution must be efficient and avoid recalculating the longest substring from scratch after each query. Lastly, when multiple queries affect the same index in succession, the solution must ensure that only the most recent update is considered when determining the result. By keeping these scenarios in mind, we can ensure a robust and efficient solution to this problem. To approach this problem, we start by analyzing its requirements and constraints. The goal is to repeatedly modify a string based on given queries and determine the length of the longest substring of one repeating character after each modification. Given the potentially large size of the string and the number of queries, an efficient solution is essential. Now, a key observation here is that modifications to the string only affect substrings near the modified index. This means we don't need to recompute the longest repeating substring for the entire string. Instead, we can localize updates to the affected regions. To do this effectively, we can use a data structure that tracks segments of repeating characters, such as their start and end indices and their lengths. This allows us to focus only on the parts of the string that change, significantly reducing computational overhead. When considering potential approaches to solve this problem, the brute force method is the most straightforward. Each query would involve modifying the string and then scanning through the entire string to find the longest substring of one repeating character. While simple, this approach is highly inefficient. For a string of length n and k queries, the complexity becomes O, k asterisk n, which is impractical for large values of n and k. Another approach is to use a sliding window. This method works well for static strings by maintaining a window over repeating substrings, adjusting the window as needed. However, when the string is dynamically updated, managing the sliding window becomes complex and inefficient. Modifications to the string can invalidate segments, requiring significant reprocessing. While the sliding window improves upon brute force for static cases, it's not well suited to handle the dynamic nature of this problem. A more sophisticated approach involves using a segment tree, which is well suited for problems involving dynamic updates and queries. In this method, the segment tree stores information about segments of the string, including the longest repeating substring within each segment, the starting and ending characters, and the segment length. Building the tree initially takes O, n, as each leaf corresponds to a character in the string. For each query, we update the tree to reflect the character modification at the specified index and recompute the affected nodes in O, log n. Once the tree is updated, querying the root node gives the length of the longest repeating substring in O, 1. This approach efficiently handles both updates and queries, with a total time complexity of O, n plus k asterisk log n, for k queries. The segment tree provides a balance between initialization cost and dynamic efficiency, making it an effective solution. The segment tree approach emerges as the optimal strategy for this problem. It leverages the principle of localizing updates to affected segments, avoiding the need to recompute the entire string after each modification. Compared to the brute force method, which is computationally expensive, and the sliding window approach, which struggles with dynamic updates, the segment tree strikes the right balance. It combines efficient initialization with fast query and update times, making it ideal for large-scale inputs. One trade-off is the added complexity in implementation, but the performance benefits far outweigh this overhead. The key insight here is the segment tree's ability to merge and split segments dynamically, enabling efficient handling of both updates and queries. This makes it the most robust and scalable solution for the problem at hand. In this problem, we are tasked with modifying a string based on a series of queries and determining the length of the longest substring composed of a single repeating character after each modification. The challenge lies in handling these updates efficiently, especially when the string is large or the number of queries is significant. To tackle this, we start by pre-processing the string to identify contiguous segments of repeated characters. For example, given the string AABC, we can represent it as segments 14AAA from index 0 to 2, BB from index 3 to 4, and CC from index 5 to 6. This representation allows us to track the ranges in characters of these segments in a structured way. To further aid in efficiency, a balanced data structure like a sorted dict can be used. This data structure is ideal because it supports fast insertion, deletion, and lookups, which are key operations needed for segment management as we process queries. Once the string is pre-processed and represented as segments, the next step is to calculate the initial maximum substring length. This is done by iterating through the segments and identifying the one with the greatest length, which is simply the difference between the end and start indices of the segment plus 1. Now, when processing queries, we first check if the character at the given query index is already the same as the query character. If it is, there's no need to process further since the string remains unchanged. If the character does differ, we split the segment containing the query index into up to 3 parts, a left segment for characters before the index, a middle segment for the updated character, and a right segment for characters after the index. Once the split is done, adjacent segments are merged if they now contain the same character, ensuring that the representation remains optimal and compact. After splitting and potentially merging segments, the next step is to update the data structure. This involves removing the old segment or segments that were affected by the query and inserting the new ones. This ensures that the data structure accurately reflects the current state of the string after the modification. Following this, we recalculate the longest substring length. To do this efficiently, we only need to check the lengths of the segments that were updated and their neighbors. This localized recalculation avoids the need to iterate through all segments, saving time. Finally, the result of this query, which is the current maximum substring length, is stored. By repeating these steps for each query, we can generate a list of results corresponding to the maximum substring lengths after each modification. The key to solving this problem efficiently lies in the insights we derive from the segment-based representation. By breaking the string into contiguous segments of repeated characters, we eliminate the need to process the entire string repeatedly during updates. The use of a balanced data structure like sorted dict enhances this approach by enabling fast operations such as splitting, merging, and querying segments, all of which are critical when handling a high volume of queries. Additionally, we employ lazy updates by skipping queries that do not change the character at the specified index, avoiding unnecessary computations. Special care is taken to handle edge cases, such as strings with only one character, updates at segment boundaries, and consecutive queries at the same index, ensuring the algorithm remains robust and accurate under all scenarios. To implement the algorithm, we rely on specific data structures and helper variables. The primary data structure is a sorted dict, which stores the start index of each segment as the key and the corresponding end index and character as the value. This structure supports dynamic updates efficiently, making it well-suited for managing segments during query processing. Additionally, we use helper variables like maxLength to keep track of the maximum substring length at any point in segments to store the current state of the string in terms of its contiguous segments. Together, these components form the backbone of our approach, enabling both efficient updates and accurate calculations. Now let's analyze the complexity of the algorithm. The pre-processing step, where we identify initial segments, takes linear time, or O(n), where n is the length of the string. Query handling, which involves operations like splitting, merging, and updating the data structure, takes O log n per query due to the efficiency of the sorted dict. Since there are k queries, the total time complexity for query handling is O k * log n. Combining these, the overall complexity of the algorithm is O n plus k * log n, which ensures that it scales well even for large strings and numerous queries. To illustrate, consider an example where the input string is AAPC and the queries involve changing specific characters. Let's walk through this example step by step to see how the algorithm handles it. Starting with the string AAPC, we pre-process it into segments, 1 4 AAA from index 0 to 2, BB from index 3 to 4, and CC from index 5 to 6. The initial maximum substring length is 3, corresponding to the segment 4 AAA. For the first query, we change the character at index 2 to B. This splits the segment 4 AAA into two parts, AA from index 0 to 1 and B at index 2. The segment 4B at index 2 is then merged with the existing segment 4BB, forming a new segment BBB from index 2 to 4. The maximum substring length remains 3. The second query involves changing the character at index 0 to O, but since it's already A, no changes are made. Finally, the third query changes the character at index 6 to D. This splits the segment 4CC into C at index 5 and D at index 6. The maximum substring length after all queries is still 3. The output for this example is therefore 3, 3, 3. Here, we begin by importing the sorted list class from the sorted containers module, which will be used to maintain the segments and their lengths in sorted order. Next, we define a class solution with the method longest repeating. This method takes three parameters, the string s, a list of query characters, and their corresponding query indices. Inside this method, we define two helper functions, add_segment and remove_segment. These functions handle the addition and removal of segments, updating both the segments list, which stores ranges of consecutive repeating characters, and the lengths list, which keeps track of their lengths. For example, adding a segment involves calculating its length and inserting it into both lists. Now, we iterate over the query indices and query characters using the zip function. For each query, if the character at the specified index in S is already equal to the new character, we simply append the length of the longest segment to the result list res and move to the next query. Otherwise, we update the string S with the new character at the given index. Then, we determine the new boundaries of the segment by expanding left and right as long as the characters match the new one. If these boundaries split existing segments, we remove the old segments using the remove_segment function. Finally, we insert the updated segment into both lists with add_segment and append the length of the longest segment to res. At the end of all queries, the result list is returned. In this implementation, we start by importing the necessary libraries and defining our solution class. The method longest repeating takes three inputs: the string s, the string query characters, and an array of integers query indices. These represent the initial string, the characters to be queried, and their respective indices. To manage the segments of repeating characters, we use a tree set called segments, which keeps track of intervals sorted by their starting positions, and a tree map called lengths, which stores the frequency of different segment lengths. Next, we iterate over the string s to identify segments of contiguous repeating characters. For each segment, we use the helper method addSegment to update the segments and lengths data structures. Finally, we initialize a string builder object to represent the mutable version of the string and an empty list result to store the output for each query. Now, for each character in query characters, we retrieve its corresponding index, check if the character at that position already matches the query, and if it does, we simply record the current maximum segment length. If the character at the query index does not match the specified query character, we proceed to update the segments. First, we locate the segment that contains the query index using the floor method of the tree set. This gives us the left segment, and we extract its start and end positions. We then remove this segment from both the segments and lengths data structures using the removeSegment helper method. Next, we handle the splitting of the existing segment. If the segment extends to the left of the query index, we add the left portion back as a new segment. Similarly, if the original segment extends to the right of the query index, we add that right portion as another new segment. After modifying the segments, we update the string builder to reflect the new character at the query index. To account for the change, we check for any contiguous repeating characters around the updated index. Using a while loop, we expand the new segment boundaries by moving left and right as long as the characters match the new query character. Once the new segment boundaries are determined, we add the updated segment back into the segments and lengths data structures using the addSegment helper method. We then record the current maximum segment length in the result list by retrieving the largest key from the lengths map. After processing all the queries, the method returns the result list, which contains the maximum lengths of repeating substrings after each query. The implementation is supported by two helper methods, addSegment and removeSegment. The addSegment method calculates the segment length, updates the segments set, and increments the count for that length in the lengths map. Conversely, the removeSegment method removes a segment from the segment set, decrements the count for its length in the lengths map, and removes the length entirely if it is no longer present. This design ensures efficient updates and queries, leveraging data structures to maintain the state of segments and their lengths dynamically. Here, we begin solving example 1 with the input string s equals ab and the query to change the character at index 4 to c. First, we initialize two sorted lists, segments to store ranges of contiguous repeating characters and lengths to store the lengths of these segments. As we process the string, we find that the characters from index 0 to 3 are all A, so we add the segment 0, 3 to segments. Then, at index 4, there's a single B, so we add 4, 4 as another segment. Finally, segments contains 0, 3, 4, 4, and lengths contains 1, 4, where the numbers represent the lengths of each segment. Now, we handle the query that changes the character at index 4 to C. After this operation, the string s becomes AOC. The segment 4, 4, which previously represented the single B, is removed from both segments and lengths. We then check the new boundaries for the character at index 4. Since C is the only character at this position, we add the segment 4, 4 back to segments. The data structures remain unchanged, with segments still as 0, 3, 4, 4, and lengths as 1, 4. Finally, we append the largest value in lengths, which is 4, to the result, giving a final output of 4. In example 2, the input string is s equals ABBA and the query changes the character at index 1 to C. We start by initializing segments and lengths as empty sorted lists. As we process the string, we identify three segments. The first character at index 0 becomes the segment 0, 0, the contiguous B's from index 1 to 3 form the segment 1, 3, and the final at index 4 is added as 4, 4. At this point, segments contains 0, 0, 1, 3, 4, 4, and lengths contains 1, 1, 3, corresponding to the lengths of these segments. We now process the query that changes the character at index 1 to C. This transforms the string S into ACBA. First, the segment 1, 3 representing the contiguous Bs is removed from both segments and lengths. We then recalculate the boundaries for the new segments. The character C at index 1 forms a new segment, 1, 1, and the remaining Bs from index 2 to 3 become the segment, 2, 3. This updates segments to 0, 0, 1, 1, 2, 3, 4, 4, and lengths to 1, 1, 2, 1. Finally, we append the largest value in lengths, which is now 2, to the result. The final output for this example is 3. In example 3, the input string is S equals ABCDD and the query changes the character at index 2 to D. Starting with an empty setup, we process the string to identify its segments. The first character at index 0 is added as the segment 0, 0, the second character B at index 1 becomes 1, 1, and the third character C at index 2 is added as 2, 2. Lastly, the contiguous Ds from index 3 to 4 are grouped into the segment 3, 4. After processing, segments contains 0, 0, 1, 1, 2, 2, 3, 4, and lengths contains 1, 1, 1, 2, reflecting the sizes of these contiguous regions. For the query, we change the character at index 2 to D, resulting in the string S becoming ABD. To update our data structures, we first remove the segments 2, 2, and 3, 4 from segments and lengths, as the C at index 2 is replaced. The updated segment for the contiguous Ds now spans from index 2 to 4, so we add the segment 2, 4 back to segments. This gives segments as 0, 0, 1, 1, 2, 4, and lengths as 1, 1, 3. Finally, we append the largest value in lengths, which is 3, to the result. The final output for this example is 3. Here, we begin by analyzing the time complexity of our solution. The first step involves segmenting the string S into contiguous groups of repeating characters. To do this, we traverse the string once, identifying these segments and storing them in a segments list. During this process, we repeatedly call the add_segment function, which inserts each segment into a sorted list. Now, insertion into a sorted list has a time complexity of O log k, where k is the current number of segments in the list. In the worst-case scenario, with n total characters in the string and all of them being unique, we would need to perform n such insertions. This makes the segmentation step take O, n asterisk log n, in total. This analysis establishes the time complexity for the initial setup of our problem. Next, we evaluate the time complexity for processing the queries. For each query, the solution modifies the string S at a specific index, which requires creating a new string. This operation takes O, n, time. After modifying the string, we determine the boundaries of the new contiguous segment by traversing left and right from the modified index. In the worst case, this traversal could involve the entire string, adding another O, n, to the time complexity. Then, we update our segments and lengths lists. This involves removing and adding segments, where each of these operations on the sorted list has a complexity of O log k. Since there can be up to n segments, this step also contributes O log n. Therefore, processing a single query takes O, n plus log n, and for q queries, the total time complexity becomes O, q asterisk, n plus log n. When we combine this with the segmentation step, the overall time complexity is O, n asterisk log n plus q asterisk, n plus log n. In the worst case, where q is proportional to n, this simplifies to O, n squared plus n asterisk log n. Now, we turn our attention to space complexity. The first consideration is the space required for our segments and lengths lists. These lists store information about the contiguous segments in the string. In the worst case, where all characters in the string are unique, there would be n segments, requiring O, n, space. Additionally, the string S itself is updated with each query. Since each update creates a new string, this also requires O, n, space. Apart from these, we use a few auxiliary variables, such as left and right, which require constant space, or O1. Therefore, the overall space complexity is dominated by the storage requirements for segments, lengths, and the string s, resulting in a total space complexity of O(n). To put this into perspective, let's compare our optimized solution with a brute force approach. A naive solution would recompute the longest contiguous segment from scratch after every query. This would involve traversing the entire string for each query, resulting in O(n) time per query. For Q queries, the total time complexity would be O(q*n squared). In contrast, our optimized solution, with a complexity of O(n* log n plus Q*n plus log n, is significantly more efficient, especially for large inputs. Now, considering different scenarios, in the best case where all characters in S are the same and the queries do not significantly alter the string, the segments list remains small, reducing add_segment and remove_segment operations. This simplifies the complexity to O(n plus Q*log n). For the average case, the complexity is typically governed by the segmentation and segment updates, leading to O(n* log n plus Q*n plus log n. Finally, in the worst case, where all characters in the string are unique and each query modifies the entire string, the complexity reaches O(n squared plus n** log n. To better understand this, we can mathematically break down the big O notation. The logarithmic factor arises from the properties of the sorted list, which guarantees O log k complexity for insertions and deletions. Meanwhile, the linear factors come from string traversal during segmentation and query processing. Together, these components justify the overall time complexity of O(n* log n plus Q*n plus log n, showing how the solution is optimized to handle edge cases and large inputs efficiently. One of the most common mistakes when solving this problem is not updating the string correctly during each query. It's crucial to ensure that the character replacement aligns with the specified query indices and doesn't overlook edge cases, such as modifying the first or last character in the string. Another pitfall is inefficiently recalculating the longest repeating substring from scratch after every query. Instead of recomputing the entire substring globally, focus on updating only the regions of the string impacted by the query for better efficiency. Edge cases are another area where mistakes often occur. For example, queries that repeatedly modify the same index, handling strings that are entirely made up of one repeating character, or managing empty strings and single character strings all require careful consideration. Lastly, ignoring performance optimization can lead to solutions that fail for large inputs. A naive approach with quadratic or worse complexity will time out when n is very large, so leveraging advanced techniques, such as segment trees or two-pointer methods, is essential for scalability. Mismanaging string boundaries is another common challenge. When working with substrings, off-by-one errors can occur at the edges, so it's important to validate all index computations thoroughly to avoid accessing elements outside the string. From an interview perspective, this problem is a great opportunity to showcase your ability to recognize patterns. Efficient substring updates often require advanced data structures like segment trees or Fenwick trees, so identifying their relevance demonstrates depth in your problem-solving approach. It's also important to discuss trade-offs between brute force and optimized solutions, emphasizing how the naive method recalculates the longest substring globally, whereas optimized solutions focus only on affected regions. During an interview, don't forget to ask clarifying questions about constraints, such as whether the lengths of query characters and query indices will always match or if there's an upper limit on the number of queries. Finally, explaining how you handle edge cases like consecutive identical characters, empty inputs, or repetitive queries can help you stand out by showing a thorough and thoughtful approach. This problem is related to several other LeetCode problems that explore similar concepts. For instance, LeetCode 424, which deals with replacing characters to get the longest repeating substring, and LeetCode 395, which focuses on substrings with at least k repeating characters, are both great practice for understanding the nuances of substring operations. LeetCode 1004 and 1156 also share overlapping techniques, such as dynamically managing substring properties or making limited modifications to maximize certain metrics. When considering alternative approaches, the brute force method is the simplest starting point. Here, you recalculate the longest repeating substring after each query. While straightforward, this approach is highly inefficient with a time complexity of O(n squared per query, making it impractical for larger inputs. A sliding window approach can offer moderate improvements. By maintaining the longest repeating substring dynamically and adjusting the window based on query updates, you can achieve better efficiency for static strings. However, frequent updates may still require additional optimizations to handle the problem's full scope effectively. For more advanced and efficient solutions, techniques like segment trees or Fenwick trees are highly effective. By maintaining information about substrings such as their length and the characters at their start and end, these data structures allow you to update only the affected segments of the string during a query. This approach significantly reduces the time complexity to O log n per query, making it ideal for large inputs. The trade-off is that implementing these structures can be more complex and require a strong understanding of how to structure and update the tree. Another approach is using hash maps and buckets to track character frequencies and their positions within the string. This allows you to dynamically update the data structure as queries are processed. While this method strikes a balance between efficiency and implementation complexity, it requires careful handling of edge cases to avoid introducing bugs. Both of these techniques demonstrate how advanced data structures can enhance performance and scalability, especially when working with large-scale problems. Great job! To wrap up, we tackled problem number 2213, focusing on optimizing string manipulation and substring analysis. We highlighted key concepts, walked through the solution, and discussed its complexity. Remember, mastering these techniques helps you excel in dynamic string problems. Thanks for joining. Don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!